Welcome, students. Today we're going to dissect one of the biggest threats to CPU performance, pipeline hazards. You've heard of pipelining now, it's time to understand what breaks it. Let's begin by setting the stage. Pipelining is the fundamental technique that modern CPUs use to achieve instruction-level parallelism, ILP. It's the reason we can execute billions of instructions per second. The idea is simple. Instead of waiting for one instruction to finish completely before starting the next, we break the instruction into smaller stages and work on multiple instructions at the same time, each at a different stage. Let's recall the classic five-stage RISC pipeline. IF, instruction fetch. ID, instruction decode and register fetch. EX, execute, ALU operations. MEM, memory access. WB, write back to register file. Think of it like a laundry system. First person loads clothes into the washer. Second person moves them to the dryer. Third folds them. Fourth sorts and puts them away. While the dryer is running, the washer can start again. This parallelism is the pipeline CPU, ideally one instruction per cycle. But as you know, reality doesn't always match ideal. Problems emerge when instructions depend on each other. Resources are limited. The program flow suddenly changes. These interruptions are called pipeline hazards. Formally, a pipeline hazard is any situation that prevents the next instruction in the instruction stream from executing in its designated pipeline stage during its designated clock cycle. Think of it as traffic congestion on a highway with dedicated lanes. When one car has to slow down or switch lanes, everyone behind it gets affected. Let's start with the most basic, structural hazards. What is it? This hazard happens when two or more instructions need the same hardware resource at the same time. Example, let's say your CPU has one memory unit used for both instructions and data. If instruction A is in the IF stage, fetching next instruction. Instruction B is in the MEM stage, reading, writing data. Both are trying to access memory simultaneously, and the hardware can't support that. So now the pipeline must stall. Wait for the resource to become available. Solutions use separate instruction and data memories, like in Harvard architecture. Add more functional units, e.g., multiple ALUs, multiple memory ports. Schedule instructions smartly, either statically by the compiler or dynamically by the CPU. Real-world analogy. Imagine one kitchen with one oven. If one cook is baking bread and another needs to roast chicken, only one can proceed. You either buy a second oven or create a cooking schedule. This is where things get a bit trickier. Data hazards happen when instructions depend on data that isn't yet available. There are three main types: a raw, read after write, true dependency. This is the most common and most dangerous. Instruction B wants to read a register that instruction A hasn't written yet. One to add R1, R2, R3. Two sub R4, R1, R5 needs R1 updated. If the pipeline doesn't handle this, instruction 2 will read the old value of R1. That's a logic error. Real-world analogy. Imagine trying to take money from an ATM before your paycheck is deposited. B, WAR, write after read anti-dependency. Here instruction B wants to write a register, but instruction A still needs to read it first. This usually arises in out-of-order execution, where instruction B executes before instruction A. 1 to sub R4, R5, R6. 2, ADD R5, R7, R8, overwrites R5 before 1 reads it. C, WAW, write after write, output dependency. Two instructions write to the same register. The correct final value depends on the execution order. 1 to add R1, R2, R3. 2, sub R1, R4, R5, both write to R1. If instruction 2 writes before instruction 1, the result will be wrong. How do CPUs handle data hazards? 1. Forwarding bypassing. Rather than waiting for the write-back stage, the CPU forwards the result from X or MM stage directly to the next instruction that needs it. This removes the need to stall in most RAW cases. Zweite stalling. If forwarding isn't possible, the pipeline inserts a bubble, a delay cycle, to wait for the data to be ready. Third, register renaming. Used in advanced CPUs to eliminate WAR and WAW hazards. It assigns different physical registers, even if instructions use the same logical register. This is the most complicated hazard and occurs due to branching. Why is it a problem? When the CPU sees a conditional branch like BEQR1, R2 label, it doesn't know whether to continue with the next instruction or jump to label until the branch is resolved, often during the EX stage. But the IF stage is already fetching the next instruction blindly. If it guessed wrong, boom, that instruction must be flushed, canceled, and time is wasted. How do CPUs handle control hazards? First, branch prediction. The CPU guesses whether the branch will be taken. Static prediction, e.g., always predict, not taken. Dynamic prediction uses history. If the branch was taken before, it'll likely be taken again. Advanced CPUs use branch history tables and pattern predictors to increase accuracy. Second, branch target buffer, your BTB, a small cache that stores the target address of recently taken branches. If the same branch shows up, the CPU can predict where to jump immediately. Third, delay slots. Some architectures, like MIPS, use branch delay slots. The instruction after the branch is always executed, regardless of the branch outcome. The compiler places a safe instruction there. Why pipeline hazards matter? Let me be clear, hazards are the enemy of performance. Every hazard wastes valuable clock cycles, increases CPI, cycles per instruction, adds complexity to CPU design. In modern processors, Intel, AMD, Apple M chips, over 60% of the design is dedicated to handling forwarding logic, speculative execution, reorder buffers, branch prediction, hazard detection. In other words, we spend more time handling hazards than executing instructions. Final thought, the invisible war inside your CPU. Every time you press a key, every time your browser loads, your CPU is running millions of instructions, and behind the scenes, a battle is taking place between instruction flow and hazards. The best CPU isn't just fast, it's smart. It sees hazards before they happen and neutralizes them before they slow anything down. And if you're going to become a system architect, a CPU designer, or even a high-level developer, you must understand this war intimately.